Yes, ma'am, you can start.
Okay, fine. So, good morning, everyone. So, I'm Subhashini, as just introduced you. I'll be covering about Module 1, 2, and 3 for the next 2 hours of session of the subject Internet of Things Technology for your 8th semester syllabus of VTU. Now, to begin, we will have discussion about Module 1, 2, and then 3. Definitely, these three modules, in order to cover with the regular part of syllabus, we at least require 30 hours. Okay, so in this next 2 hours, I'll just be briefing about what are the key aspects you have to look into the syllabus and which are the important questions from exam point of view and what is the knowledgeable content you have to extract from it. Okay, so this 2 hours of session definitely will be a compressed one than your normal classes. And now let's begin with the module 1. First module of your syllabus is completely the basics on Internet of Things. Okay, so to have an overview about the topics in the first module, we have totally of 2 chapters in the first module. The first chapter comprises of all these points what we have to discuss on. Okay, so this will be the agenda for the first module's first chapter. Let's go on with the discussion on, before entering to the complete content, we will have some knowledge on what is internet and what is a thing. How do you define these two, right? So, as you all are already familiar with internet, okay, see, internet is basically a basic knowledge which networked component is required, okay? Today the whole world is completely dependent on internet. Okay, we are not able to do anything, any part of task without internet. So when you say what is an internet, define an internet. When you say definitely internet would be inter-network, correct? So it is an interconnected computer network which basically makes use of the standard protocol, which is a TCP bar IP. Okay, so if you say internet is a network of networks, we have multiple types of networks. Basically, you know that we have LAN, MAN, and WAN. And apart from that, there are many other subtype of networks. We have PAN, personal area network. We have storage area network. We have body area network. We have field area network, right? So there are multiple types of networks. These networks, can we enable them to communicate with each other? Yes, it is through internet. So internet pumps serves as the major definition in the component of IoT, Internet of Things. The first term we require definitely Internet IoT, right? So we will look into deeper aspects. As of now, from the definition point of view, Internet is nothing but it's interconnected computer networks, which basically makes use of global TCP/IP protocol suite. Now, moving on to the next component of this IoT, definitely it is a thing, right? So now I would just pause a minute for here in the slide. Okay, so what is a thing basically, or generally when you refer it in terms of English? Okay, so the English meaning of this thing is nothing but any object which has its own existence in an environment. Okay, so any object that exists in an environment with its own mass, with its own weight, with its own physical structure and shape, we call it as a thing. Okay, but that thing is not something what we refer to in IoT. In IoT, the thing is a normal object which we define generally, but that object should be embedded or should be attached with certain components or equipments in order to make it a thing of this IoT. So you mean to say the general thing what we say in our English terms, okay, what we normally find around us as things, those all things can't be taken as Internet of Things. Okay, so when we say a thing, in order to make it involved into the IoT, we have to perform some changes to that normal thing. Okay, like say for example, I have a pen with me. The pen, by raw, it's a general English thing, right? That pen has its own weight, it has its own structure, it has its own functionality to do. That's a general English thing. Now, that pen, can I tell it as a thing of IoT? No, I can't directly make the raw pen to be stated as the thing of IoT. So, for which all I have to do is I have to embed this normal raw pen with certain components. So students here, the general part, which is not there in your syllabus, I'm just telling you, in order to make a general thing as a part of Internet of Things, we have to attach certain components to it. What are the basic components which a thing should require in IoT? Okay, a thing of IoT should require basically a physical object attached with a processor or a controller, followed by a converter, and sometimes it can have its own memory, and then it should have actuators or sensors attached to it. So these are the four minimum components which are required for any general thing, English thing, to become thing of IoT. Am I clear? So to make a physical object which is directly referred to as English word thing, in order to make it as thing of IoT, we have to attach at least these components. The first one, you should have a microcontroller or a microprocessor. And the second component, we need to have converters, maybe analog to digital converters or digital to analog converter. And we require sometimes its own memory if it is necessary. And sometimes on the last one, the component is basically a sensor or an actuator. So let's see what are these components. Why do we require them? Why does a physical object require all these things to make it a thing of IoT? Okay. So basically, if you can see the coming part of slide, what is a thing? When we say things can be anything what you require. It can be a computer, it can be a mobile phone, it can be a raw sensor, it can be actuator, and many more. I couldn't put it up all the components in the slide. The general question is, Madam, can I make any normal thing which I see around me as a thing of IoT? Can I do everything? Yes, you can do it, provided I told you we have to add on these components what I have told. Okay. Generally, by raw, I can't make it smart. I can't make it a thing of IoT. Coming to these were the two major components of IoT. One is internet and the other one is thing. We require both of these to make it complete package, right? So we at the most require IoT, internet. We at the most require a things. Okay. So internet, as you can see, and you see it's a novel paradigm because it's the one which is gaining interest across the globe. Okay, and definitely IoT is not a standalone type of technology because it is again collaborated to multiple technologies because of because of this IoT. Maybe it's connected to cloud computing, it's even connected to big data, it's even connected to data analytics, right? So there are many fields. It's even connected to your machine learning. So all these technologies, what are evolving, they are collaborated with each other, right? So they don't have their own individual. They can't function as a standalone. That's the meaning, okay? And you can see it's a novel paradigm. It's of course into the bloom, okay? And you can see here what are the basic ideas of this IoT implemented in IoT. You can see the presence of variety of things or objects. As I told you, these things are not the normal English word of things. They are smart things, right? Okay. And you can see that these objects, whatever we have, the object here is nothing but a thing. Those objects can perform all these jobs. Okay, they can see, they can hear, they can perform their functionalities, they can sometimes even interact. Okay, and they all have to collaborate to work for a common task, right? So that's the basic idea behind connecting multiple things over internet. Why do I connect internet of things? Definition says connecting things over an internet work. Connecting things over internet work. Why should I do that? We have a goal. To achieve that goal, I require multiple things connected over internet to work on together, right? And you can see because of this IoT, these objects as general English things, they are becoming what? Smart, right? To make them smart, definitely we can't directly make them smart. We have to add the four components what I told you, right? And you can see that some of the examples what you can find of a thing: thermostats, then heating ventilation system, then AC monitoring system, controlling ACs. Basically, we call it as HVAC systems. Okay, yes. So these HVAC systems are all what we see at our homes, right? So these are nothing but some of the examples in which we have things which are smarter. Okay, those things, smart things, communicate with each other. You can look into the definition of IoT. Definitely, students, we have a variety of answers to it. Okay. as you can find, Internet of Things provides services in all these areas. You can just look at in terms of A's. If you can remember these things in terms of A's, multiple A's. Okay, anytime, any content available, anyone and to anybody, any service and any business, any part, any network, any place, anywhere, anything, and any device. So services of this IoT is available in all these forms of A's, multiple A's. So we can say it as A's, right? Internet of Things could be elaborated in terms of 6 A's, which you can find in the slide. And one more thing, see IoT elements. Definitely for this IoT, we require internet and we require things, right? So if you can just check out combination of all these things are these elements basically, right? So if you can see identification of a thing, okay, and we have sensing equipments, then we have communication network required, then it should do certain computations, it should bring out certain services, and it should define certain rules, right? So all these things is put together is what we call as IoT. For namesake, I can just tell you it's a collection of things connected over internet. But in reality, to connect these things over an internet, why should we do it? All these things, all these tasks are to be required. Okay, so it's a collection of all these activities. All these activities should be done inside an IoT, right? This is again the term. And if you can ask me, like IoT, who coined this term when it was popular, right? So for this, we have the next topic, which is genesis of IoT. So when we say genesis of IoT, it talks about how did this IoT term evolve, when did it start, and what was the changes, what were the evolutionary steps taken on in this IoT, right? So if you can say the person, the inventor who coined this term IoT was none other than Kevin Ashton. So he was a scholar working for MIT, and during the year 1999, he has coined this term. This term was brought into existence, naming Internet of Things was a term coined by Kevin Ashton. But the study says that the term Internet of Things was coined by him, but the concept existed long back, before even 1999. So, what I meant to say, the term was coined by Kevin Ashton, but the concept of this Internet of Things, how does it work, was all beyond. It was before the term was coined, right? So, properly, if you say the term originator was something none other Kevin Ashton. And you can see his prediction was something like this during 1999. Okay, so though it was predicted as Internet of Things in 1999, it took out its bloom. It took out its bloom after 2008, right? The large number of users, drastic number of things. Apart from users, see, till now, people were the one who were consuming internet for a variety of purposes. Now, even things are consuming internet. Even things are connected over internet. So you can see the strength is increasing abundantly, right? Now, if you can just find out the definition or the what prediction of this Kevin Ashton long back. Kevin Ashton, during 1999, he predicted something like this. A statement was given this way: computers were brains without sensors. Computers are sensing things for themselves, right? That means without human intervention, okay? And they were able to perform the computations by themselves. So this was predicted long ago, and now definitely it's into picture. It's beyond it, right? A machine goes beyond working of a human certain times, right? Coming on to the evolution of internet. So when I told you, definitely for Internet of Things, the most internet significant picture. Now here, internet, how all did it start to evolve? In the sense, when was it intended to build? Very beginning. What was the main intention? Why did they start this internet? At the beginning, do you think they did have any idea to connect even things also? No, 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 never. Right? So they had earlier certain picture of connecting only the machines of research scholars working for the Department of Defense. Okay, so network, before internet evolved, network wasn't a picture. That network required at the minimum two or more systems to connect. Then it further evolved to internet, telling multiple systems of different networks. The systems of different networks were connected to each other with the help of the earlier version of internet, and later on, mobiles started joining this network, right? This was termed as mobile internet. And furthermore, when you move a bit more, your PCs and your mobiles, along with the people. Okay, so these all were the networked equipments. And now what you can find along with person, along with mobile, along with his PC, multiple other gadgets involving even your things are enabled to be connected over internet. So this is what the evolution of internet is, right? So earlier it was internet for only systems, and now you are like in a position that you can connect anything, whatever you can find around in your surroundings, making it smart and enabling it over internet. You can connect them and you can communicate with them, right? So this is nothing but evolution. And from the exam point of view, students, you will have to be writing this diagram talking about the evolution of internet in terms of purpose. So this tells about the applications, the diagram, and this diagram talks about the purpose of internet in terms of evolution. If you can observe here, the graph goes beyond in the way of x-axis. You can see earlier, very beginning, internet was mainly intended to establish only connectivity. Okay, and later on it moved on to networked economy. See, when I mean connectivity, it's nothing but two or more people, if they want to chat with each other, if they want to share certain files with each other, that's nothing but connectivity. And moving on to network, this means about trying to gain certain income by having this internet work. Okay, so basically here it's nothing but what you say transactions. Okay, I make some communication with the help of certain transactions so that I can earn money over internet. So you can see certain applications of these. In terms of economy, we have e-commerce, we have digital supply chain, we have collaborations. So these are certain examples of applications where you can gain economy using internet. See, this is the purpose. Purpose is slightly deviating. It was slightly changing. Very beginning meant for only connections, and later on it moved on to making money, and then it moved on to enabling multiple people, multiple societies, society level, at your even cloud level, and even your streaming applications were being enabled in the third case. Okay, so it was enabled with even streaming applications, and now in the fourth case, definitely all these three along with enabled with multiple things wherein data comes into picture. Please imagine students, see the person people to people communicating per day. If you take up your WhatsApp application, if you take up your Facebook application, you imagine per day how much of data you receive in the form of messages, pictures, audios, videos, etc. Right? Okay, how much of data you receive and how much of data you are going to send per day. Please take an estimation of it. Okay, and definitely for a month you take per day, per month, per year. If you take up an estimation of data, how much of data is getting generated only by the people across the globe, right? Now that marks an end. Please think of people no more. Next, you talk about the things. Okay, even things are generating the data, right? People are only heavy. People's data is not able to get managed and maintained, because of which we moved on to certain other technologies. Imagine about the data, even it's adding on with the things. Right? So bulk not bulk term what I'm using is not at all enough to think about the vastness of the data generated by all these things, right? You have people, you have processes, you have data, you have things. You have to handle all these things, right? Especially the data, when you speak about it, is nothing but what you can say big data. Why do we call it as big data? Because of these things only, right? People moved out, even things are generating data means how, where, and in what way to handle, right? That's about actually the speaking of this is genesis of IoT in terms of internet's evolution. Now, moving on to the next term, students, we have something as a connection to IoT and digitization. What are these two? How are they connected? See, when we say digitization, both are actually different terms. Okay, but one is required for the other to be how. As I already told you, IoT is things connected over an internet, and they are trying to share the data, they are trying to compute, they are trying to bring out certain results. Now, when I speak about digitization, why is the term digitization coming here? Okay, digitization purely is a technology in which The data needs to be generated, needs to be stored, needs to be processed in purely digital form. Okay, so digitization is nothing but the process of making any type of data converted into digital. What? Maybe for further computations, maybe for storage, maybe for doing certain actions immediately. Okay, so why digitization is required means, if you take about the example of your telephone networks, I'll just come to the telephone networks now. Okay, now what happened in your telephone networks? If you speak about the very old telephones, okay, where you had certain ring like numbers, you would have seen them in English pictures, right? Ring like numbers, you'll have a receiver and then you'll dial in, right? Now those type of phones, if you speak about, were you able to message? No, messaging ability were not available in the primitive or the earlier type of phones which were analog by nature. That means analog type of phones can't store your voice, can't store your data. Data is nothing but through phone. What is my data? It's my voice, right? Whatever I speak. That data were not capable to be stored. They were not capable to be forwarded. They were not capable to be what? Edited and so on, right? Now, in order to store analog type of data, see, we have two types of data, as you all know. I don't think I have to say on that, analog and digital data. Analog data can't be processed, they can't be stored. Okay, they have to be processed on time. They can't be stored and they can't be retrieved later because they are analog by nature, right? In order to make that analog data to get stored, we require digitization. Okay, so now in terms of IoT, as I, if you could find here, in terms of IoT, we may require computations to be done. We may require the services to be stored. Okay, so in order to do this, definitely we require digitization. The data, whatever is being generated in IoT by the things, need to be digitized because they may be required for further computations, not maybe immediately. Maybe after 1 year, I'll have to compute something. Okay, so that time if I need the data, they need to be stored. Okay, and if the analog data are available, then they can't be directly stored, right? So they need to be converted to digital form. That's nothing but what you say, connection between IoT and digitization, right? You can see here, best examples of this digitization is, students, what you can find, the whole what photography, the whole what field of photography is completely digitized. That's why you can see earlier when they captured the phones through cameras. Okay, what happened, I mean, when they captured the photos through cameras, they would take at least certain hours or maybe sometimes a day to bring out your hard copy of the photograph, right? But today, what you can see is you can capture them in the phone itself and you can immediately print it to the printer and you can give it, right? And today's cameras are of high end that they immediately capture, they immediately bring out the hard copy immediately within seconds, right? So this is all happening because of digitization. Okay, and that's one example of the field which is completely digitized. And also you can see transportation industry. See why transportation industry is coming as an example of digitization. You can say about, for example, booking an Ola cab. Okay, yes, Ubers and all these vehicles. What you have, whenever you need, you order them, you book them, they are available to you in the service. So this thing is all happening because of digitization factor. So IoT is purely dependent on this technology called as digitization. Today, most of the technologies are digitized. Everywhere you can see, because of the computations enabled and because you can extract data anywhere, any point of time, it is all because of digitization. Okay, this is another different point. Now, coming to IoT's impact. Okay, this would be the next topic. Impact of this IoT, as you all know, it is very moving out. You can see this survey is being taken for the end of 2018. Okay, it tells about how much 17 billion of things are connected over internet. Okay, so you can just see Cisco predicts that by 2020, that is for this year, it will be reaching around 50 billion. Please imagine things, not the people. Please forget about the people. We're talking about only things. 50 billion of things will be connected over internet. That means what? 50 billion things are connected, 50 billion things for 1 second, how much of data they will generate for 1 second. Please think of how much of data they'll generate and where should that data be stored. And today we don't have only things, even people are generating data, even things are generating data, where they should be stored, where they should be computed. What about the security, right? So all these are nothing but some of the thoughts which come into picture. This diagram will give you a significance of the impact of IoT. Please observe, along the x-axis we have the year, and along the y-axis we have the device count in terms of billions. Okay, please observe, very beginning during 2003, the Internet of Things was on very beginning margin position with one person with one device connected over internet. Okay, and as you move on to 2008 and so on, I told you, the bloom of IoT significantly changed from 2008 onwards. So you can see from here onwards the point started to reflect in multiples, correct? So you can see from 2010 person to two devices count exceeded the number of people. Okay, things count exceeded the number of people, and you can see around by 2020, as per Cisco's prediction, it says that it will be how much? For one person, you will have at the most of 7 to 8 devices. That means what? Things are more connected over internet than the number of people. Okay, so that's nothing but you can see that, right? There, totally, if you speak about 50 billion objects connected over internet, means per person across the global population, per person you'll have this much of average number of things connected over internet, right? So this is the of your IoT, how quickly it is growing, how quickly it is building on, right? Now, moving on to certain applications of your IoT, where all are they applied? Definitely, I need not tell you students because you are almost in the end of semester, okay? And you would have done a lot of projects on IoT. So I just quickly go through whatever you have in your syllabus. Definitely, the content only available in your syllabus is not limited to, okay, it is far more beyond than that. Because I'm constrained with time, I'm taking up only the syllabus point of view. So here is the first application of IoT, which is connected roadways. The best example is in terms of roadways for transportation. You can see self-driving car of Google, right? So this is the picture. So this stands as an example, best example, remarkable example of your IoT application, where you can find a given automobile will be comprised of multiple number of sensors of different varieties. It will have its own controller. It will have its own actuator, right? And it will have certain own memory to implement its different part of system. See, the whole component, when I say by default a car by default is not an application of IoT, right? Because car is an object, car is a physical object, it has its own task to do. Now to make it smart, to make it work smart for me, to make it a thing which of IoT is required, I have to add on certain components that will be added with. Definitely, what do you think? In a self-driving car, will we add only one sensor and one actuator? No, definitely not. By default, an automobile will have around hundreds or thousands of sensors, right? So if you can see, even the driving car is more than it, right? More than thousands of sensors. And what we need is definitely these sensors, what I'm embedding into the automobile, they all need to be enabled with IP. This is the major point which we have to note on in smart or self-driving car. Okay, they need to be IP enabled. That means the sensors have to communicate over the network. That feature is required. Okay, so that with these type of communications, what we can do is a self-driving car may need to communicate with another self-driving car or another vehicle moving around the road, right? Or a car want to communicate with a traffic light or traffic signal. So these things can be enabled as an extension to your projects. Now, in the same roadways, in order to construct this Google self-driving car, the challenge face, please observe here. What are the challenges? You need to look into the safety, right? You need to look into the mobility factor. You need to look into the environmental factor. So what does this mean? What are these things, challenges you have to take on? That means, see, uh, definitely driverless cars there, right? If there are driverless cars, how well you will assure the safety, okay, of the passenger who is moving inside it, or maybe the one who's walking outside on the way, right? How will you assure the safety? These challenges need to be considered while, when you're constructing or implementing these type of projects over the roadways. Similarly, you talk about mobility. So when I say, if I have to move on to the certain destination, Okay, how quickly or how fast will I go? How fastly will I travel? And how will I deal with objects coming as obstacles along my way? Right? So these things have to be taken on in mobility factor. Coming on to the environment. Now, in case of environment, if you speak about other in terms of emissions of the vehicle, okay, is it emitting a lot of harmful gaseous leakages, or is it going green? All these things need to be taken into fact, right? So I can construct my own implementation way in different forms by attaching different sensors, but looking into all these aspects is what is required for roadways and in terms of challenges. Now, similar to connected cars, okay, of your roadways, it's not only car, it can be any automobile. Okay, one example is self-driving car. And similar to it, you can have one more project of roadways, which is nothing but IMA. Please observe, student, IMA is intersection movement assist. This is happening across circles. Like say where you have multiple roads meeting at a point, okay, there we require this sort of project, intersection movement assist. What does it do? What does it do? During the point when you meet up with any signals or circles, okay, whether you are violating the traffic rules or not, okay, whether you're following the rules or not. So these things will be alerted to you. Okay, so in case if the vehicle is moving out of the signal, or in case if it is within the signal, then those intimations will be led to you, will be led to the passenger to be known, or it will be led to even to the driver to be known, right? In case of driverless, it will be led known with the passenger. So these sort of IoT. Okay. Now, see, the next part what we have is industry. Okay. So connected cars in terms of transportation is one example. And the next example is in terms of industries. In industries, how this IoT is playing out its role. Definitely it's turning on to a major bulk, huge portions or much of the industrial sector is what they are consuming effectively the use of IoT. How? You can see the evolutions of IoT. I think most of you would have heard about it, right? So industrial evolutions, if you speak about, earlier it was only assisted with mechanical purpose, and then later they thought into having mass productions, bulk productions, and then they put up embedding your electronics and control equipments wherein the productions were automated. And now we have integration over IoT with Industry 4.0. What is this? That means they are integrating IoT into the industrial evolutions. That means IoT sort of workings, IoT sort of behaviors are all brought into industry totally to what? To make it more effective, and in order to make its production with much of automation. Okay, so these things are all required, and industry is definitely making use of IoT. In the vast application, vast benefit of this IoT is made use by your industry. Definitely, we as a user, we may make use of it to a certain extent, but industries are the one which are grabbing the much use on it. Another example. IoT is nothing but at homes. How do you make use of it? One example. See, students, here we can find only certain examples. Definitely, these are not the complete examples. Every area it is touching out. I'm just briefing you with it, right? So the next example is digital ceiling. Here you can find digital ceiling when I say at my home or at my room. Okay, my ceiling has to be digitized with the help of different components, and those components have to communicate with each other. Like say, for example, I go out on a bright sunny day. I go out, come into my room. Okay, as I step into my doors have to automatically open for me, and when I enter my door into my room, then the sensors have to sense my temperature, and they have to tell whether you require more heat or you require your body to be cooled, depending upon which your heater or your coolers or your ACs will be turned on, and sometimes your lights will be turned on, right? So all these components communicate with what? With internet. Okay, so these things should communicate over internet. Please remember this. And most of you will have the confusion of automation and IoT. Are they both same? No, definitely not. Automation is a different concept. IoT is a different concept. But automation is involved in IoT. Okay, please observe, students. Most of you have this confusion. That means any type of project wherein human is not there and it is doing by itself means it's an IoT project? No, never. Okay, please think IoT project says human involvement is not there, definitely, but things should have to communicate over internet work. Okay, individual thing, if it's like say for example, if you take up your calculator, okay, take up your calculator. Calculator I press certain buttons and I perform some, it gives me the result. Can I say it's an IoT? No, it's just an automated device because it performs calculation by itself. That's it. But it's not a component of IoT because it's not communicating over internet. It is not storing its data somewhere into the cloud. It's not doing any other part of communication to any other device over internet, right? So like this, please make a margin of difference between automation and IoT. Definitely in IoT we have automation, but not all automations are IoT. Let's take that into clear picture. Now here in the diagram, I'll not just quickly go through it. Please observe we have different type of things. These are the different type of things. I have lighting systems. I have sensors for these different components, and I have built-in automation. I have HVAC. HVAC is humidity, ventilation, and ACs. Okay. Then I have cameras, and I have certain Wi-Fi devices. Why? I need to connect all these things, right? These all devices have to communicate over a network, so I require an access point. So all these devices are connected over each other and they are controlled by a central network controller. Network controller, maybe an infrastructure, a box like thing. Here is nothing but a connector, or it could be a particular switch, or it could be a particular hub, you can say. Right? Now, all these components connect with each other and they will serve me. Okay, so this whole component set of controls coming under digital ceiling, they act as an IoT project because they do communicate over a network. Okay, so network means need not be that they have to communicate over LAN only, they have to communicate over WAN only. No, not necessary. Any type of network they have to communicate. Okay. And moving on to the next example, see, IoT can be used even in wearables. Okay, yes, or smart creatures, you can say. What is this example? So if you can find, this is an example for a smart creature. You call it as smart roach. It's actually looks like a cockroach. Okay, it's called as a smart roach. This was mainly a project of IoT. Its purpose was to penetrate into the disasters and look into survival of people. That means, like say for example, if a place is met with an earthquake or certain disaster, okay, and if somebody is stuck inside a huge building, okay, and if they are still living, how will others get to know? How will the people get to know, right? So for which they make use of this device, it can penetrate into smaller holes, just like cockroach does, and it can sense whether any living organism or any living body is available inside that particular spot. Okay, so that can help you to rescue, right? This is an example for smart roach, in the sense smart cockroach, right? So this is an example of implementation of IoT. And just like these things, we have even connected ears. Okay, so ear like structure into the shape of a cow. Okay, into the ears of a cow, what we can do is we can attach a small sensor like type, and what we can do, we can try to monitor the behavior of an animal. We can try to see its theft activities if any happening. Okay, so observing the behavior of a particular animal especially, you can go on with the devices like this. That means they can even be attached to your body as well. Okay, attached and detached to the body as well. So they are called as smart wearables. This would be another area or applications of your IoT. So this is the part discussion on applications. Let's move on to the last topic of this chapter, which speaks about difference between two terms, IT and OT. Okay, students. So IT, as you all know, is information technology, and OT is operational technology. Okay. So what are the differences between these two? Array, madam, why are we studying about this? Definitely, IoT is combination of these two again. Okay. IoT requires information technology as well as operational technology. Now, I'll quickly tell you what are the difference between these two. Okay. Now, see, when you want IoT to implement, definitely what you will take, you require internet network, and then you require things. Things are nothing but any objects, right? You make it smart by attaching a processor, sensor, actuator, and so on. You require those components, no? Right? So who produces you those components? Who manufactures those components? They are coming under the component of OT. Okay, so one who is involved in what producing the operational components. Okay, one who is involved in controlling the devices. They are nothing but the part of OT. And what does IT concentrate on? See, IT concentrates on basically this device, how much data it generates, what data it generates, what type of data it generates, how should we format it. right? How should we send it over the network? This thing is concentrated by your IT. Please observe, IT concentrates on how to handle your data and how to communicate, whereas OT concentrates majorly on the physical objects or the devices which are operating or which are functioning. Okay, so at the device level is what we have as OT, and the data level is nothing but your IT. So that's what you have in the picture. Please observe. IT organizations, what they do? They basically take care of data in different forms. It can be through emails, it can be through files, print services, databases, and so on. So basically, it handles your data. And here you can find, here you can see they are nothing but basically the devices. The best example here, what they have taken for IoT is SCADA systems. See, SCADA systems is supervisory control and data acquisition system. So this is a project, and this project requires a lot of components of IoT. They are basically meant for what? Observing something's behavior, acquiring data from it, and making further studies. Okay, so observing anything it could be, right? So that particular intention is what your SCADA system looks on, and it requires a lot of components for it. These all components come under physical operations, which is a part of operational. Okay, so that's actually the difference. If you can just observe in terms of behavior and detailed point of view, these are the differences between IT and OT. If you can just observe. OT, operational focus in terms of industrial OT network and the enterprise IT network. So if you can just check out, here we say OT for industries, IT for enterprise level, as you all know, because industries build the devices, enterprises look into the aspect of data. Hmm? Operational focus, if you can say, among these two, definitely, which should be running in mode. Okay, the physical device has to run, then only we can have data from it, correct? Unless the device runs, can we have data? No. So it needs to operate. OT has to operate 24/7. Okay. This, what about this, madam? IT need not operate 24/7. Yes, definitely, even that has to be done. But in order to have data, we require the components to be running, right? Physical devices should run. So that's the thing. But what you can say now, say for example, I have a server. Okay. What is server we use? We store our data and we retrieve data from the server. That server should run morning to evening, evening to morning again, correct? So if that server is not able to run, can I take data from it? No, even if it pauses, like say your results, video results, okay, sometimes the server goes down. Will you be able to extract your result? No. So the device has to function, device has to be on. So OT is required to be on for 24/7. Okay. And in terms of priorities, if you just check out, availability is requirement of availability is more in OT. Then these are the priorities, right? If you say about priorities, first priority will be top one, the last number will be the least one. These are the priorities, and depending upon types of data, if you can just check out here, the types of data are different, right? So data type, data forms are different, whereas type of data in OT network is totally different. Format, these formats are totally different. And in terms of security, definitely at different levels. Here you concentrate morely for security over data at the network, whereas you concentrate security of the accessibility to the devices. And in terms of failures, different, they are totally different, right? Here you talk about basically networks, here you talk about basically the devices. Failure devices, I mean, what are they concentrated on? All these things will differ. Next, you speak about network upgrades. Okay, so network upgrades, are they required frequently? Are they required frequently over here? When are they required? So you can find it here. So I'll share the slides, and maybe the contents will be made available to you by the organizer. And last point, you talk about security vulnerabilities, how prone they are, okay, how frequently prone they are to attacks. Okay, this is nothing but security vulnerability. So if you can speak about in terms of networks, the security vulnerability is very high, because in terms of IT networks, anybody can try to prone any type of attack to the data. Whereas in terms of devices, unless you know the physical functioning, unless you know the architecture of the device, you can't directly prone an attack, right? So the security vulnerability is low in case of OT, whereas vulnerability is very high in case of IT. Vulnerability means how frequently you are prone to attacks. Okay. Some of the differences of IT and OT, very important question, students. And moving on to the last part of the chapter, it's IoT challenges. Very important question. If you can speak about what all are the challenges you have to look look into in IoT. Very nice point. So if you can just see, the first topic is on the first challenge, that is scaling. What is scaling exactly? Scaling means how much to how far extent can you add the number of devices in IoT? Just as we told, IoT definition says interconnecting things, right? Do we have any restriction on the count, madam? No, we don't have any restriction to the count. We can add n number of devices to the network, correct? So that's nothing but scalability. And apart from only things or devices, can we add people also into it? Yes, by all means. Right? So scalability is the major challenge. You have to look into it. Definitely, with name you can tell I can add n number of devices, but look into the behind factors. When you add more number of people, it's tough to manage. It's tough to monitor. It's tough to give security. Correct. So these things is what coming under scalability is. Okay. And definitely when I say here internet you are using, that means you need to look after your IP address also. Correct? More number of devices are using, the more number of IP nodes getting existed into the network. How will you maintain them? Okay. That's another point on scalability. Now, moving on to the next point, which is on security. Definitely, this everybody would have known, right? When I say thing getting connected over internet, who knows that thing can be itself a malware, right? The thing can be itself injected with some malicious code and it could have been injected into the network. So we need to track into all these things. And what happens when a new thing want to enter the network? Can we let it go? Can we let it come in directly? We should have some authentication mechanisms, right? So those things are all coming under security. Next, we talk about privacy. See, definitely, once thing generates data, how is the data going to be stored? Where is the data going to be stored? Okay, and how secure is my data? Right? So these things are coming under privacy in terms of data security. Okay, and moving on to the next challenge. See here, you can find big data and data analytics. That means what? Things are more because of scalability factor. Now, because things are more, huge data is getting generated. Huge means I can't even tell in the terms of count. I can't tell in terms of units of GBs or in unit of zettabytes. Okay, it's beyond that. Okay, so that much data, if it is getting generated by multiple devices on multiple projects of IoT, then how will I handle that huge amount of data? And how will I take the data whichever I want, whenever I want? On what basis is the computation done? How quickly will I fetch the data over such a huge volume? Okay, in such a huge volume of data, how will I fetch whatever is wanted for me? How quickly will you do that? So all these things is coming under the next challenge, big data and data analytics. And last one is nothing but interoperability. So when I say interoperability, not all things are same by their feature, correct? Not all networks are same by their feature, correct now? Yes. So each network has its own feature, has its own speed. Each protocol has its own okay, its own syntaxes. So interoperability speaks about how will I cope up with different formats, different protocols, different architectures in order to work together. So these are the challenges which you have to look into while implementing IoT type of projects. Done, students? With this, we come to end of chapter 1 of your module 1, right? So questions, I think I'll be taking at the end of the session. Is it okay, sir?
Yes, ma'am. We'll be taking it at time, ma'am.
Yeah, because we'll be running with shortage of time, right? Let me cover up the syllabus, then we'll questions at the end. Okay. So next part of the chapter, module 1, as I said you, it's of 2 chapters. So first chapter is completely on the terminologies and applications. Now let's quickly go on to the second chapter of module 1. So the second chapter here you'll be discussing about the architectures which are available to implement this IoT. Okay, so majorly these are the important questions that you can find as well in the topic. Okay, nothing deviating to it. So architectures, what are the preferable architectures you have to implement your IoT? Before going to architectures, you can see this question is again an important question. What is it? The drivers behind network architecture, in the sense, what made you to come out with this new architectures in IoT? What factors made you to come out? In the sense, again, these factors are similar to the challenges what you have seen just now previously, correct? So these challenges itself made you to bring out with different architectures. okay, in IoT. So same thing, no, whatever I told you just now, scalability, extending your network, security, as you know, and constrained devices and networks. Please observe, in IoT, things are constrained, devices are constrained. What do you mean by constrained? They are limited by their functionality, correct? So take an example. I told you just now, a pen. A pen can be made as a thing of IoT by making it smart, by attaching some sensors or actuators, by attaching certain processor to it, by attaching certain converters to it, right? I'll make it smart somehow by attaching all these components. Now you compare this pen, which is smart, along with your mobile phones. Huh? Can you even compare it? No, mobile is a general purpose system because it is able to perform multiple tasks. Whereas my pen, it was intended only for purpose of writing, yeah, nothing else. Hmm? So that's nothing but constraint feature. Constraint feature, when I say it's limited by its functionality, I can't what easily make it to perform different type of tasks. Easily, I can't do that. Okay, so that's called as constrained devices. And the next thing is you have constrained networks as well. That means networks are enabling connectivity. See, there are two types of networks coming in IoT. One is for connection of devices, and other one is for communication of data. Okay, I'll tell you the later parts. As of now, please observe. Constrained networks means to connect these devices. Okay, networks what we are using are very much constrained. We will look into it detail later parts. Okay, as of now, these are nothing but some of the aspects which made you to come up with new architectures. As you can see, huge volume of data getting generated and support for legacy devices. What does this mean? Legacy devices means which are not intended to be smart. Okay, in the sense a very old type of things, very old type of devices which are not intended to be smart. They're not smart. Okay, so even such devices, can you make it smart now? Yes, we should make it. We should not throw it away, right? So all these things supporting for legacy devices, how this modern devices communicate with the older devices or existing devices or even outdated devices. So all these factors finally coming to data analysis, right? Whatever data you have in huge, how do you perform analysis in real time? For that moment, you're generating data in huge, and for that moment you want results. How quickly, how is it you're doing it? Okay. So all these points led to the what? Point of coming up with different architectures. So two of the best known architectures you have in your syllabus for IoT. One is one M2M IoT architecture and other one is IoT World Forum. Please observe these two. No, I can just tell you to compare with OSI model and TCP/IP model. It is like this. Okay. Please observe it. Okay. So you have for networks OSI model and TCP/IP model. The same way for IoT also two best well-known architectures you have. One is one M2M and IoT World Forum. So among these two, one M2M was started first, in the sense it was brought into implementation first. Then today we have in bloom or in run IoT WF architecture. So let's look into the features of these architectures, which is an important question, students, as you can find. So you can just find that this one M2M was majorly started with an intention to have common service layer. So they wanted service layer to be separate in the part of implementation. So the new architecture called 1M2M was mainly intended to focus on separating the service layer. Okay, so let's see how the architecture looks. Please observe here. You can find here, see, there are three basic layers. Okay, one coming up with the high-end application layer, other one coming up with service layer, and the third one coming up with the network layer. So they categorized basically in one M2M architecture, the three layers. One is application, service, and network layer. So here we have to majorly look into the service layer. Okay, in one M2M. What does application layer do, Madam Andre? Definitely, this application layer is nothing but for the part of interfacing, how human interact with your project, and how does he start activating the services. So those things are coming under application layer, talking with end users perspective. And network layer talks about definitely how the data which is generated is being made to store, and how is it made to be replayed, how is it communicated over other devices. Those things is what your network layer talks about. Moving on to service layer, what does the service layer talk about? As you can find here, service layer encompasses different communication devices and hardwares, different communication networks, different communication technologies and protocols, and a common service layer. Service layer is made to be common, whereas you can find these implementation layers are different. So totally all these different implementations should work together to give out a common service. Okay, so these services need to be passed out between application and network layer. They have to interact with each other. Okay, so this is what is the main intention of one M2 architecture. Now, moving on to the next type of architecture, which is World Forum, it gave a much clear what classification to the different layers. Okay, so totally unlike your OSI reference model, even this layer has 7 layers in it. Okay, as you can see the bottom of layer is nothing but operating at the hardwares. Okay, basically the physical devices and the controllers, which are microcontrollers. And next you see you have connectivity, edge computing, data accumulation, abstraction, application, collaboration, and process. So process, collaboration coming at the high end, right? Let's see the features of these things. If you can just look out what is the first layer, bottommost layer, which are physical devices and controllers. So when we say in IoT, physical devices means they're nothing but things. As I told you just now, thing means not general English thing. They are things of internet. Okay. So you see, thing is nothing but the basically device equipment. And if you can say things, what do they do? Okay, they are endpoint devices, or sometimes they can even be sensors. What does this thing do in an IoT? It can send or it can receive an information. Things of IoT, they can do only these things. That's it. They can either send something and send the information, or they can receive from somebody else as an actuator. And these things, features, they differ in size. Okay, they differ in their ranges. Okay, how they can be very small, minute sized thing, or they can be even giant machines. Okay, so in the sense, size will differ for these things, not an institute. Okay, and what is the primary function of the thing? Thing is what generates the data. In thing, we will have a sensor. Okay, and that sensor, basically what it does, it senses something and senses something. That something is nothing but your data, sensed data, right? So in IoT, who generates data means it's your thing and especially your sensor, correct? That's nothing but the first layer. Now, moving on to the second layer. What is the second layer? It's connectivity layer. What does it do? It establishes communication between layer 1 devices. What are layer 1 devices? Things. Okay. So for communication, we require this connectivity between the different devices. And along with providing communication, it enables reliable delivery of information. What do you mean by reliable delivery? It talks about error-free delivery of information. Okay, error-free delivery of information. Your data is assured to be sent over a network without any errors. And you can see it also performs switching and routing tasks, which is nothing but forwarding and finding a reliable path. Okay, and it also performs translation between different protocols, because I have different layers. In different layers, I have different type of protocols implemented. So in order to cope up with different protocols, I require this connectivity protocol, and also it provides network level of security. Now, moving on to the third layer, which is edge computing. Students, this topic is a bit interesting. Okay, so you see, what does this edge computing means? Edge computing talks about performing computations at the edge level. Now, what do you mean by edge in an IoT? Edge in IoT means it is nothing but your thing, or it's nothing but your users. Correct? Huh? So now, at the thing is generating data, correct? Now, at the thing level, if I want the computations to, then I require edge computing. See, to tell it is very easy, but to implement it's very tough. An edge, a thing or a sensor. Please think of a sensor. You would have seen sensors, as per my knowledge, right? So I'll show you that sensors, very small units there. Now, can they perform computations? Sensing only is big for it, right? Can it perform computations at a huge level? Mass data computations can it perform? No. Because of that only we have gone for cloud. What happens is in normal IoT scenario, things generate data, senses the data, and they'll generate data. That data will go to the cloud and will be stored. And we will have a computation center. They'll be computed either at the cloud level, or they can be computed at the edge level, or they can be computed at the fog level. There are 3 levels actually. We'll discuss that in the further parts. Edge level, fog level, and cloud level computations. When I say computation means, it's nothing but you use the data, you perform some computations, calculations over it, and bring out the result. It's not the storage. Okay. Please don't think about storage. When we say about computing, the data which is generated by the things need to be calculated. Some computation activities you have to do on it. And then you have to bring with some results. Where are these calculations done, madam? So you can have 3 levels of calculation what stages. One, you can do calculation at the cloud. Second, you can do calculation at the edge. And third, you can do calculation at the fog. Okay. So among these three, which is close to the thing, madam? Which is close to the thing means definitely edge is close to the thing. Okay. So you can see it does, what is it? What does it do? What does it do? It evaluates and reformats data for processing at higher levels. It filters the data to reduce the traffic, and it accesses the data for alerting the notification. So accessing the data for alerting means what? Here the action you have to do is alert. Alert based on what? Some computation has to be done. So that is done at edge nodes. So these are the 3-layer implementations. We told totally about 7 layers, right? So 4, 5, 6, and 7, what do they do? Data accumulation, as you know, accumulation talks about gathering the data, capturing and gathering the data and storing it whenever you need. Okay. And data abstraction layer. What do you mean by abstraction? Abstraction talks about, see, different data are getting generated by different types of sensors. We have multiple types of sensors. Okay, moisture sensor, humidity sensor, what is it, soil sensors, right? Environmental sensors, then, right? So you have multiple types of sensors. So these sensors generate data in different formats. Not all data will generate in same format. So these different formats of data need to be collected and they need to be brought out into common format. That's called data abstraction, and that is not known to me, right? As a user, I'll not be knowing about all these things. That should be hidden. So it is called as data abstraction layer. Next, you speak about application layer. Definitely, this layer is the one with which I will interact. I, as a user, will interact. So it's basically the application providing end view. And the last one is collaboration and process layer. What does it do? It shares the information between different applications. So again, even this is at the end user's perspective. All these are nothing but the layers of IoT World Forum architecture, right? Very important question, students. And if you can see here, in terms of IoT World Forum architecture, how does IT and OT differ in this case? So please observe the small difference here. Okay, in terms of IT and OT, please observe. IT is query based, whereas OT is event based. Difference. What do you mean by this? IT is query based and OT is event based. That means what? See, when I say IoT project, data is getting generated by whom? By the thing. What is that thing? It's basically a device. Correct? Now, device comes under which category? OT. And whatever data is getting generated by the device, it comes under what? IT. So, what I do with the data, I usually query the data. I'll store it, definitely. The data which is getting generated, I'll store it somewhere. And after storing, whenever I need, what do I do? I query it. So, IT is basically query based. Whereas OT, when will data get generated? When the device is running. That means what? Some event has to occur. So, it is called as event based. Got it? And the same way, next difference. In IT, the data is at rest, whereas in OT, the data is in motion. What do you mean by this? Madam, I am a thing. Right now, I'm sensing something. Okay, I'm sensing. So when it senses, what happens? Data gets generated. What happens to the data which is generated? It will communicate over the network and it will get stored somewhere. It should move, correct? It will not remain there itself. It will not remain in the sensor itself. Correct? So the data which is sensed by the sensor will move. So it is called as data in motion. It will move and it will get stored into some server. Okay. And when it comes and stores in the server, now it is part of IT. So it is at rest. Got it? Next difference, IT and OT. So IT's data are all non-real-time data because they are already stored from long back. I don't know from what time, right? So they are non-real time. Whereas OT, the data is real time because right now the device is functioning. When functions only, data will get generated. And that's a real-time data. It's happening in real, right? So that's nothing but differences between IT and OT in terms of IoT World Forum's perspective. Please observe here. Those are about the 2 major architectures which are implemented for IoT. Okay. Now, this is a general scenario. That means any type of IoT architecture you design, it should have it should have these layers. That's what it means. So the heading is simplified IoT architecture. It's not named with something else because it tells that any architecture you can implement, either one M2M or either IoT World Forum, or you come up with architecture, it should have commonly these layers. That's what it says. Okay, any architecture it can be. You can build your own architecture, provided it should have these three layers. What are they? Please observe. It should have a core functional stack. Okay, and it should have a data management and computation stack. Two stacks have to be there. One is functional stack, and other one is data management stack. Please observe what do you mean by this functional stack. It should have applications, it should have communication network, it should have physical devices. Please observe these are physical devices. I hope were there in the previous two architectures, right? So even here you have those three. So any architecture should have those three. Now coming to the detailed diagram description, the same diagram is given in detail here. See what you have in application. I have different applications. I have analytics over here. In communication network, I have different types of networks and application layer protocols. And last one is nothing but your things, sensors, and actuators. They are nothing but physical devices. Okay, so networks can be of all these four forms. Applications can be of any of these applications. Okay, so let's see in detail one by one. Okay, first layer. What is the bottommost layer? Physical devices. Definitely, we already discussed about it. Things layer means what do they do? Things layer nothing but physical layer things. So things differ in their structure, shape, and their functionality. Same description. Coming on to the communication network layer, please observe communication network layer is classified into sub-layers, four sub-layers. One is network management layer, network transport layer, gateways and backhaul networks, and access networks. See, four types of networks you'll find, not just one network. Please observe that. Okay. Now, coming on to the first factor, I think I can skip this slide because it's already discussed. Things, when I say they can be sensors or actuators, these things can be of different forms based on these factors. You can observe actuators can be battery powered or they can be power connected, right? Andre, you may require a battery for it, or you may require a power source to plug in and play. Okay. Or sometimes it can be mobile or static. What do you mean by mobile or static? They can be in an environment where they have to move or they may have to remain there only. Okay. And next one, low or high reporting frequency. What does this mean? Low or high reporting frequency means uh, how frequently they are going to report the data. Then simple or rich data. That means complexity. How much of size are they going to get generated? Report range. How far can they send the data? How long can they send the data? How distant? Okay. Then object density per cell. This means how many sensors can be put together in a given area. So all these nothing but other factors on what physical devices. And here is a diagram which just tells you that you have four different forms of varying nature of access. One is in terms of mobility and other one in terms of so the devices can be arranged in terms of these four forms where you can have sometimes low mobility. If you're having low mobility, you may have low throughput. Sometimes with low mobility, high throughput, vice versa. Four combinations depending upon these two factors, mobility and throughput. So these four arrangements are nothing but four different scenarios wherein your project can be set up with respect to physical devices. Now, coming to network layer, as we told just now, please observe all of you. This networks, whatever you can find here, no? Yes, find here the names of these networks, and this is nothing but the range coming in it. Okay, NFC, one range, less than 10 centimeters, networks coming under, and less than 5 kilometers, these are the other types of networks. What are these networks? See, these networks are nothing but they are nothing but communication networks. Communication network, connection networks, both are different. Connectivity network means, see, I have some physical devices. Let's say I have some devices, some sensors. I have to connect them. To connect, I can't use these networks. Okay, so for that we have connectivity networks separately. Those we'll discuss later. These networks, why do I require means in order to send the data which is generated, the data which is generated by the device, that data, if it has to go somewhere and get stored, then I can use all these types of networks. You can find the name of the networks here. I'll not go into detail. Okay, so these networks is what we require for communication. What communication? Data communication from one device to another device. Okay. Whereas, please observe, uh, next type of networks, what we require is gateway networks. Gateway network means a gateway to gateway, firewall to firewall. Okay, a separate network has to be set up. Those networks I can use this. Please observe. I can use WiMAX, I can use Ethernet, I can use Wi-Fi, I can use 802.11 AH, and these things. They are nothing but for what? To connect only the gateway to gateway, right? And next one, what we have is next in the next part of the discussion, there we have things. How do we connect, madam? For that, what type of network should I use? So you have different type of networks there. We'll discuss that. Okay. So this is about a small description to network layer. Now coming to application layer, here you should know the difference between these terminologies. What are they? Analytics and control applications. Andre, analytics applications are different. Control applications are different. Control applications looks on with their functionality, whereas analytics application looks on about how to handle data, how to perform computations over data. That's what is the concentration on analytics. Control is different from analytics. These differences you have to know. And what do you difference between data analytics and network analytics? These two differences you will have to know. Data analytics is different. Network analytics is different. In network analytics, I talk about bandwidth requirement. I talk about collisions. I talk about the data rate. Whereas general data analytics talks about its size, its structure, its semantics, its formats. Those things is what we concentrate there. And also, how do we associate or how do we connect this data analytics with business benefits? These two has to be known. In a sense, using this data analytics, how do I achieve profits in business? And followed by the last one, smart services. How are they different to all of these things? Smart services, what do they mean? Right? So these things is what you have to discuss under one component of the simplified IoT structure, which is functional stack. Now moving on to the next structure, which is data management stack. What happens in this data management stack? Please observe here. In data management stack, I talk about basically these requirements. What are they? How do I minimize latency? What do you mean by minimizing latency? Less time taking in order to extract data from a huge volume. That is minimizing latency. Then conserving network bandwidth. See, simply, I can't consume more and more amount of bandwidth from the network, right? So how do you reduce the space? How do you conserve the bandwidth? That's another important task you have to talk about in data management. Then increasing the local efficiencies. Efficiency, how do you improve? So for this, you can just check about there are three layers to implement. One is, please observe, the data centers. Huge data where they can be stored. Either they can be stored at the data center or the cloud. Either they can be stored in certain what databases, core network, or either they can be stored at the devices itself. Okay, so they are nothing but endpoints. Please observe, at the device, if I'm storing the data, it's nothing but endpoint. At certain between cloud and endpoint, I have something called as core network, and to the end you have cloud. So this part talk about cloud computing. This part is nothing but fog computing, and this part is nothing but edge computing. Please observe, this is the level: cloud computing, fog computing, edge computing. When I say among these three, which is close to the devices, definitely close to the devices, edge computing. What about cloud? It is too far, madam, but it is definitely useful because this is a place where you can store huge volume of data, whereas these two are not that huge. Perfect. That's the thing, but another difference what you can find. And see, same things. Okay, the bandwidth is very limited, so you have to conserve it. Latency can be sometimes high, correct? So sometimes even your gateways can be unreliable, so you have to look into the reliability factor of your gateways. And looking at the volume of your data, it is definitely huge. Okay, you have to take care of replicas, you have to take care of unnecessary data. Okay, and big data, huge volume of data. How do you handle this? So all these things come under data management. Okay, so after this, the next important question is fog computing. What is this fog computing? As we just told, please observe here, fog computing. We have cloud computing at the end, we have core IPv6 network, and here is what you have, the fog, right? What is this fog computing characteristics? Please check about. It has low latency. Why? Because you need not go to cloud, far more to the cloud, right? You need not go to the cloud, and you can store somewhere between or close to the end devices. That's nothing but fog computing. You can do computations close to the end devices and not moving to your cloud. And it is geographically distributed. That means what? The applications or the services of this fog computing is distributed across the globe. Okay. And it is deployed close to the endpoints, but not at the endpoints. It is close. Okay. At the endpoints means it becomes edge computing. Next thing, you can see there are different wireless communication protocols between the fog nodes and the IoT endpoints. IoT endpoints means things, sensors or actuators. For computation at the fog, we require separate nodes. They are called as fog nodes. Okay, so there is communication between the fog nodes and the IoT end devices, and they are used for sometimes real-time interactions, right? So this is the thing, but fog computing's benefit. Whereas cloud computations, no, you can't use it for real time because it takes delay. Understanding. Fog can be used for real-time interactions. Similarly, edge computing, which is much reduced in latency. You can see here computation is done at the edge, where preferably at the sensors. Okay, sensors only sense the data, sensors only compute the data, and at the sensors only you'll compute and get the results. That's called edge computing. Okay, so you can see that we have new class of IoT endpoints to do this task. Okay, normal devices can't do it. We have some certain new classes of IoT devices to perform this computations. Okay, so you can just see example computation at the electric pole itself. Okay, in the electric pole only you're generating the data and you're computing there only. Okay, so that's called fog compute. I mean, what is it? That's nothing but example for fog computing. Whereas computing at fire hydrant in manufacturing industries, at fire hydrants you're generating data, and in case if you're met with the fire, will you wait for the data to be stored into the server and then perform computations? No. I get some instant reactions there, right? Once you got to know that you're meeting with a fire accident, then immediately you will have to respond to it. You need not wait for computations, go to store and then bring the results. No. So there are but example for edge computing. Okay. These two examples, and here is the hierarchy of these three layers. One is edge, fog, and cloud. Please observe topmost layer is cloud layer. Between that you come with fog computing, and then bottommost is nothing but your edge layer. So edge layer is always close to the sensors or the devices or the things. Okay, is nothing but the hierarchy of edge, fog, and cloud, how they are located. So if you can see which is low latency rate, low latency is your edge layer. Then a bit medium is nothing but your fog. High latency is your cloud. Okay, but doesn't mean that cloud is very. I mean, it's not of use. No, no, no. Cloud you can store huger and huge volume of data. Here you cannot store that much of data as compared to a cloud in these two layers. But computation time is reduced. Okay, you have to compromise one or the other. All right, that's the end of module one. Okay. And now let's go on to module two. Okay. So module two is complete description on the smart objects used in things, which are nothing but sensors and actuators. Now we will see what are these sensors, actuators, and their features. Okay, smart objects followed by sensor network. Okay, so sensor, basically what is a sensor? It's a device which is meant to perform sensing activity. It can sense anything, any physical quantity that converts measurement reading into digital information. See, digitization is definitely required because sensor, after sensing some real quantity, what it does, it converts the data into digital form. Okay, it has to do this. And once you convert the data into digital form, what it does, madam, it can send it to any other device. Okay, for transformation into some useful data. It can send it to a controller or it can send it to any other device for performing certain actions, right? It's nothing but sensors activity. And moving on to type of sensors, there are different categories of sensors as you can find: active or passive sensors, right? And invasive or non-invasive depending upon the type of environment where they're used. Okay, and if they are associated in the environment where it is to be set up or need not be inside the environment, then you call it as invasive and non-invasive. Contact or no contact, like say if you want to measure some activity, should the sensor be attached to the device or not? That's called contact or no contact. Then you have absolute or relative. Should it give the measured values exactly, or should it round it up, or some relative measurement is okay depending upon that. Then you have area of application, where are they used, which area. And last one is what type of data do they measure. Okay, physical, what is the physical quantity which it measures, right? So these are nothing but different categories of sensors, what you have. Different sensor types. We don't know, just different types of sensors. So here you can find types of sensors and what are the examples, followed by the description. Okay. Small sensor. This picture is told to you because sensors are definitely electronic equipments. Now, are they biodegradable? Yes, some sensors are biodegradable. So here you can find a sensor which is dumped or put into the soil. Okay. So it is mainly used to measure the sensitivity of the soil, moisture content in the soil. And this sensor, it is purely a battery driven. Once it is out of your battery, what it does, it degrades by itself into the soil. Okay, it will not be an e-waste anymore. Okay, so what happens is electronic components, most of the electronic components will be after their time of use, term of use, they will be no more used. They are used as a scrap. They may be recycled. But this device, it gets degraded into the soil. Okay, so there's no need to worry about environmental hazards caused by this sensor. Okay, so this is nothing but a biodegradable sensor, what you can find, and this was developed in this university, NDSU. And if you can say sensors, okay, how many types of sensors you can find in the smartphone? Not just one or two, there are multiple types of sensors. If you can find the round picture here, mobile phone, a simple smartphone, if you can say it has a lot of sensors in all these ways. These all are the names of sensors that you have in it. Okay, you can just quickly go through these type of sensors. And now you can just see here is a chart. It's of no use. It's just a survey for you to know how much of sensors are in use right now. It's a prediction for up to, you can just find 2030 to 2037. 2032 survey says that this is the count of number of sensors. Okay. Yes, please find it out in terms of millions. Okay. Please find it out in terms of millions. You can see the survey or the growth rate of your sensors is definitely drastically increasing. We are somewhere over here, right? We are somewhere over here, and definitely even in further more years, it will grow up. This is the rate treated by the T sensor summits. They have given the survey chart. Sensors will definitely be in use in the higher further years. Next component in IoT is actuator. What is this actuator? They're nothing but acts. They act. Okay, sensors sense, these act. That means they are opposite to the sensors. What do? They take some information from somebody and they perform action. Whereas sensors, what they do? They send some object and send the data. Whereas actuator take the data from somebody and they perform the action. Okay, that action can be in terms of motion, in terms of force, and any other activity. Okay. So here is the example for connection between these two. Please observe here. So you have a physical object. I'll place a sensor to it. Sensor measures this physical object and senses the data and gives out to digital representation. That digital data is again passed as input to the actuator, and actuator performs the action again with the help of physical object. Okay, actuator, how will it perform the action? Again, it requires some action component, physical object to require, right? So that's nothing but chain or connectivity between sensor and actuator. Here is a scenario which connect our body to the components. Please observe, in our body, we have the 5 major sensing organs, correct? They're nothing but sensors. As you can find, the 5 major sensing organs, eyes, ears, nose, mouth, tongue, and then hands, right? The skin, what you can say. So these are nothing but your sensing organs. These sensing organs sense whatever we can, okay? And it passes to the controller. Who's the controller in our body? The brain, okay? So that brain, on sensing something, it performs certain action. What somebody pinches you. Let's say somebody shouts at your ears. Okay, the moment they shout at your ears, will you keep quiet? No, you perform some action, right? Either you run away, or either you walk out, or you stop that sound with your hands. Limbs. Limbs are nothing but actuators. Okay, and brain is nothing but the controller or the processor, and sensors are nothing but sensing organs of our body. So please observe sensors, CPU, and then actuators. So this is how our body is also acting like your particular components. Okay. Now, classification of actuators. What are the types of actuators you have? You have based on type of motion, based on the power they acquire, based on the type of stable outputs where they produce, based on the area where they are used and based on the type of energy, right? Classification. And here you can find some types of sensors, types of actuators. These are the types of actuators followed by their examples. Now, next component which is used in a thing are MEMS. What are these MEMS? MEMS stand for microelectronic mechanical systems. So what are they basically? See, they are nothing but combination of electric and mechanical elements. Okay, that means they have both in it. They have sensor also and they have actuator also inside it. So that they only perform sensing and they only perform acts. Okay, so they are basically preferably of low cost devices, if you can say. Okay, and where are they used? Preferably these MEMS were being introduced first into the automobile sector. Okay, the best example in automobiles were your airbag systems. So in airbag systems, what do you have? You have the whole system treated as a single project in airbag accelerometers. The whole project is one single system, and that airbag system has sensor come actuator inside it. Both it has inside it. So then nothing but what you can say MEMS. Okay, and other also you can have micro pump MEMS are available in printers. Okay, and even your phone has MEMS in the form of accelerometers and gyroscopes. So here is an example of a MEM device. It's a TRA. Okay, TRA stand for torsional ratchet. So it's a mechanical equipment. So here is the view. Okay, a pictorial view of this particular actuator. How does it look? Now, moving on to the next component. In IoT, thing is said to be smart, correct? So, when is an object said to be smart? A physical object, when is it said to be smart? A physical object is said to be smart when it has these four components. Please observe, it should have these four characteristics. One processing unit, it should have a sensor or actuator, it should have a communication device, and it should have a power source. Please observe these four other components. I think I already told these four components are definitely required for any object to become smart. Otherwise, by default, it's just an object. It's not a smart object. Okay. So I think I need not explain about these descriptions. They're already familiar. Here's the diagram with all the four components. You can see sensor, actuator, communication device, then power source. Why is the communication device required? Because the data, whatever is being sensed, okay, that has to move on from one device or one equipment to another equipment, right? For which we require a communication device. Maybe from this machine itself, it has to go to some other device. So we require communication device. And what are the trends in smart objects? Definitely, size is decreasing, very much trendy in nature, and power consumption is reduced. Processing power is increased. Then communication capabilities are increased. Okay, and communication is being standardized. These are the trends. And moving on to the type of networks, we have sensor networks and wireless sensor networks. SANETs and WSNs are the two types of networks used in IoT. Okay. Definitely, when we say SANET means it's nothing but connection between different sensors and actuators. So connection, you can connect all of these sensors also, you can connect set of actuators also, you can connect. They are called as SANETs. So these SANETs, definitely they are resource constrained because we have not bulk of or huge varieties of sensors can be connected, but sensor is a constrained device anyhow. So the devices found in SANETs are definitely resource constrained. Okay, so for this we have one example of SANET, which is HVAC system. I told you HVAC is humidity, ventilation, and air conditioning systems. Here you have sensors come actuators for performing heating, for performing ventilation, for performing air conditioning. Okay, so this HVAC actuators are all connected to the temperature sensors. So this together forms a SANET. Okay, temperature sensors along with HVAC actuators together, when I connect them in a network, they form as SANETs. So nothing but, and some of the advantages and drawbacks of SANETs are given here, right? Great deployment function, then simple scaling, low implementation cost, long-term maintenance, reduction in cost of number of nodes, okay? Then better equipped to handle dynamic changes in terms of topology, easily adaptable to changes. Then drawbacks are potentially less secure. You need to have some authentication technique into it, and low transmission speed, and they are influenced by the environment. Okay. Next type of network what we have in IoT is WSN, wireless sensor network. So what does this do? Hmm? WSN, as I told, it's again a type of network, what you find, wherein different sensors are connected over wireless fashion into a network. Okay, and they are easily flexible by nature. You can see some of the features of this WSNs are low memory, they are lossy communications, narrow band media, power consumption is critical, and moderate CPU power. So these are nothing but some of the features available in WSNs. Okay, with respect to the same components, he has told it. Just same thing. Okay, limited processing power, limited memory, lossy communication, limited transmission speeds, and limited power. These things are nothing but some of the constraints. So we told SANETs as well as WSNs are constrained because we have constrained nodes. Okay, since we have constrained nodes, these are the constraints, limitations. You have to either overcome it or you have to patch up your components or work according to this constraint resource or environment. Okay. So nodes which are found here are called as constrained nodes. Definitely, they are constrained by nature. And last discussion, what we have here is sometimes sensors can aggregate the data. Okay, that means what? See here, I have here 1, 2, 3, 4, 5, 6. 6 sensors I have. Okay, they are reading temperature. Let's say they are temperature sensors. You can see each temperature reading is different. Okay, over a given environment. Now, should I take all the 6 temperature readings separately? No. Sometimes what happens is, depending upon your environment, what I can do is I can place an aggregator. Okay, what does that aggregator do? It takes average of all the temperature readings over a given area of different sensors. Okay, and it can take only the average one than having 6 different values. Okay, so that's nothing but additional operation what you can perform using a sensor. So I can perform aggregation using a sensor, and here is the scenario. So this can be enabled only if all these sensors are networked. Okay, all these sensors should be networked, and then only I can perform aggregate of their readings and take it away. Okay, that's nothing but another feature. Now, last point, if we speak about wirelessly connected smart objects basically have two communication patterns. One is event driven and the other one is periodic. What do you mean by event driven? Event driven means I sense the information and I'll not share it. I'll not send it unless somebody asks me. Okay, that's event driven. Periodic says you need not ask me, as and when I sense, I'll immediately send, or I'll send it for 1 hour, or I'll send it for 2 hours, or I'll send it for 1 minute, or I'll send it for 1 second. Getting it? So sensors or the objects connected in smart objects connected in wireless networks, they can send the information based on events, or they can send the information based on periodic fashion. Periodic fashion means you need not make a request for the data. The device automatically sends you the sensed data for every period it has set. Whereas event driven says, unless you trigger with a request, I'll not send you any sensory information. That's nothing but event driven, right? This part is nothing but the complete smart objects description with all these components, sensors, actuators. Then you had smart description. Then you had SANETs, followed by wireless networks, right? Now, the next module, which is module 3, standing for IP as IoT network layer. So what is this chapter concentrating on? See, first module was completely on basics with its architecture and basic definitions. Second module was completely on smart objects. The third module is completely on how IP is significant in IoT. As I told, IoT is nothing but Internet of Things. Internet, when I say to come, because internet is incomplete without IP. IP is the protocol which runs in internet. IP stands for Internet Protocol, right? Here in this chapter, we'll discuss about definitely business case for IP, in the sense why IP is suitable for business activities, what is the need for optimization and what is optimization, and something like profiles and compliances, what are they, and how do you optimize the IP for IoT. These are the topics highlights for the chapter. Let's go on first with business case for IP. What is this business case for IP? Business case for IP talks about how IP is benefiting industry. Okay, I think by this time you would have known the importance of IP, students, right? So these are some of the important points or benefits of IP for Internet of Things. In Internet of Things, IP benefits what all purposes? Okay, you know that IP is open and it is standard based because IP has a significant standard, right? Okay, and it is versatile, commonly available for any type of devices connected over internet, and it is ubiquitous standing for availability of the service at any point of time and in any place. Okay, and it is scalable, able to accommodate multiple number of devices. It is manageable and highly secure because associated security features inside it, IPsec, what we call, okay, and stable and resilient. It means what? So any type of errors, any type of what do you say, mm, changes happening with respect to topology or with respect to network bandwidths or with respect to congestion variations. So all these things are nothing but to be handled. You can handle all these changes in case of IPs with these factors. Okay, it is stable and resilient. Then consumers market adoption, that means what? So you can say that earlier or the existing type of devices and even your modern devices, both of them can make use of IP. You can communicate older with newer version of devices. And last one is innovation factor. Innovation factor talks about changes in IP. Okay, the changes in IP definitely are made at frequent intervals and they are updated to everybody and they are standing as innovative factors. So these are some available to internet of things by IP. This is an important question. So we have two models used in IP for IoT. One is adoption model, another one is adaptation model. What do you mean by adaptation model and adoption model? Please observe, very important. Adaptation, generally in English, adaptation means what? You have to somehow adjust, right? So you can see that some devices in IoT are of non-IP and few are of IP type. Okay, IP type means they support internet protocol and some devices are there which don't support IP. Clearly existing and they were not designed so. That means can I throw away those things? No, I can't do so, right? I can't throw away the existing type of devices. So for which what I can do is I can take up the existing protocols. Okay, one sec. Yeah. So what I can do, I can take up the existing type of devices which are non-IP and I can take up IP devices. I can establish communication between these two. So that's nothing but adaptation model. So in adaptation model, I make use of these type of devices. ALGs we call it as. These ALGs will what communicate between non-IP and IP devices. Okay. Whereas what is the second model? Adoption model. So what does this adoption model do? It tries to convert all the non-IP layers to the IP layer. So this is nothing but translation. You're translating. Okay. So adoption talks about converting or replacing non-IP layers with IP layer. You're making modification here. Hmm? And, if you can take an example of these two type of adoption models. So first one, adaptation model is what we discussed. For adaptation model, we have example of SCADA systems. Okay. And also we have example of ZigBee solutions. Okay. So ZigBee and SCADA systems are the two examples for adaptation model. What do we do in adaptation model? In adaptation model, we use certain intermediate devices. What are they called? ALGs. What does this ALG do? It translates non-IP to IP. Okay. So in SCADA, we find separate interfaces, gateways we call them as. And here also we call it as ZigBee gateways in ZigBee. Okay. So these gateways convert non-IP to IP for adaptation. Right. Now, for choosing which model is good, madam, should I choose adaptation or adaptation model? Yes, that decision is done based on the following factors. What are the following factors? Depending upon the direction of data flow, if it is bidirectional or unidirectional. Okay. So depending upon the direction of data flow, you can choose among these two which model is fine for you, right? Okay. So this is what one discussion talks about. It just tells different classes of IoT devices you have with different type of data size what they are sending. Now in that case, how do you adopt these two models? First case. Okay. So in the first case, for bidirectional and unidirectional, definitely if the data is bidirectional, you are sending and receiving, then what type of model suits you? Okay, whether adoption or adaptation. And in case of unidirectional, which direction, which model suits you? One classification you can do based on data flow directions. Other one is overhead involved in the last mile communication path. That means for long distance communications, what is the overhead involved? Depending upon this, you can make a choice for adaptation is good or adoption is good. But factors which you have to consider for which model is good. Hmm? And other one, depending upon the data. So what type of data flow your model you are using? So depending upon that, also you can choose either adaptation or adaptation. Okay. And different categories of networks, what you're using. Okay. If you're using multiple categories of networking devices followed by different categories of networks, then I can go for which type of model. So these are nothing but some of parameters choose for which model is suitable. The next important topic in the chapter is for optimization. Why should you optimize IP for IoT? Okay. I should optimize IP for IoT because of definitely constraint nodes. I need not explain these points. I think it's well understood. Okay. Optimization means the changes what I have to do to IP in order to make the device work into IoT. Okay. So I have to definitely do because the devices are constrained. I have to do it. Okay. And you can see devices are constrained with all these things. Constraint means definitely, in terms of processing power, in terms of power issues. Okay. So all these are nothing but are constraints, if you can say. Hmm. And you can see constraint in terms of what? Resources. Constraint in terms of infrequent transmission of data. Constraint in terms of security and management issues. Okay. And constraint with respect to power. Constraint to strip it down IP stack. That means non-IP layers are available. Okay. So because of all these factors, they are constrained. And also you can see constrained with respect to computations when compared to general PCs. If you compare your PC to the normal IoT device, definitely there is a lot of changes, you can't even think of comparison these two, right? So these are nothing but some of the comparison activities or overheads what you find. Okay. And also, you need to optimize IP for IoT because of even constrained networks. Devices are constrained, networks are also constrained because the networks are not high-end networks. That means devices are constrained. To establish network among these constrained devices, we have networks also of constrained type. Hmm? Constrained networks, if you can say, they are limited by power as well, and they are limited by bandwidth as well. Okay, so they are constrained in this way. Here, the even PDR value varies. PDR is packet delivery rate. It will not be consistent. It will keep varying. So even these things are all okay. And also, you know that IP versions need to be considered because we have two major versions of IP, V4 and V6. Okay, so we need to optimize IP for these two as well. Okay, some devices may support IPv4, some devices may support IPv6. So still we have to enable communication among these two. You can find here. So some main factors for support from IPv4 to IPv6 are first one, your application required between IPv4 to IPv6. Then we require support from your cellular providers, correct? And we require support from serial communication because when I'm establishing communication in serial fashion, bit by bit transmissions, to transit from IPv4 to IPv6, okay, I need to make use of certain sockets, right? The socket support is required. And also I require something called as adaptation layer. So adaptation layer is basically required for IPv6 layers, especially. Okay. In case of constrained nodes, I require this IPv6 adaptation layer. Coming on to the picture, please observe here. What is the role of this adaptation layer? What does it do? Please observe. The adaptation layer resides between network layer and data link layer. What does it do? It optimizes IP for making it available to the other two layers, bottom two layers. Okay, so IPv6, IPv4 residing in network layer. These devices, if we have to optimize it for the lower bottom two layers, then we require adaptation layer. So it's a modified or it resides between these two. In order to optimize IP to IoT, I require standards, certain standards. What are the standards? 6LoWPAN to 6Low. 6LoWPAN is the first one and 6Low is the second one. These two are nothing but some of the standards available for optimizing IP into the IoT. Please observe what is the 6LoWPAN and 6Low. 6LoWPAN is the first example. So all these standards are defined under RFC. What does RFC mean? It's a request for comment. Actually, request for comment is nothing but it is available from IETF. IETF is Internet Engineering Task Force. Okay, so this standard defines any protocol, any rules, and any regulations are being dumped in a note or in a publication. That publication you call it as request for comment. Okay, so even the standards what we have, description to the standards, their formats and all are described in RFC with certain numbers. Okay, they'll give certain numbers. Now, 6LoWPAN's basic focus was to optimize only IPv6 packets. Okay, so it optimizes only IPv6 packets over constrained networks, and it falls into this particular standard IEEE 802.15.4. Here you can find difference or the changes what you can find in terms of IoT stack for 6LoWPAN. Please observe, this is the normal protocol stack for IP, and this is the varied protocol stack for 6LoWPAN. Please observe what is the change you can find here. Between network layer and data link layer, I have 6LoWPAN residing because it acts as my adaptation layer. This is to optimize IPv6 for your bottom two layers. Okay, instead of adaptation, I have 6LoWPAN. 6LoWPAN acts as an adaptation layer. It will with the help of its own standard and structures. Please observe, these are the three header stacks for 6LoWPAN. Okay, 6LoWPAN header stacks. One is for header compression, for fragmentation, and for mesh addressing. Yes. Header compression, if you can just see, I'll quickly go through it. Header compression talks about reducing size of the header in 6LoWPAN. Size of IPv6 header 40 byte header size and 8 byte of UDP header size is reduced to how much? 6 bytes combined in some use cases. So you can just see the size of header size is quite reduced for both TCP as well as UDP in case of LoWPAN. And also you can find that amount of this is not required. Now come to this part. How much size is being reduced? Please observe here. This is the original size of your IEEE 802.15.4 frame. Okay. And you can see that this full length, what you can find, UDP size of 8 bytes and IPv6 of 40 bytes. Please observe, it's completely reduced. UDP size is reduced to how much? Almost of 4 bytes. And 6LoWPAN header with your IPv6 40 bytes completely. So what you can do, what is the benefit of reducing header is you can increase the payload size. Okay, that's the benefit in 6LoWPAN. So it is optimized. And also you can find that in the fragmentation, what's this fragmentation structure? Please observe. In fragmentation, we have totally three fields. One is fragmentation header, datagram size, and fragmentation offset. Okay, so this is nothing but structure of fragmentation header. And even here it says that the fragmentation header totally it's found to be how much? 2, 3, 4, and 5. 5 bytes of fragmentation header is just used for case of 6LoWPAN. Even fragmentation length is being reduced. That's the meaning. And also we have addressing in terms of mesh addressing. What does this mesh addressing in terms means? In order to specify the source and destination address fields, okay, for transmission of your data from one hop to another hop, the amount of space consumed is very less. It says that preferably how much? You can find that 2 to 1. 5 bytes of space is being used for specifying the addressing fields. Okay, so this is nothing but reduction in terms of header size for header fragmentation and addressing fields. If you reduce this, your payload will be of huge size. That's the meaning. Now, you have a difference between two terms here, mesh under and mesh over. So what do you mean by mesh under and mesh over? So you can just see mesh under is a term used for forwarding the data from one node to another node, but it uses a complete single IP hop. Whereas mesh over, okay, is nothing but the part where you have data link layer to be involved. Usually routing is done at which layer? Network layer, correct? So if you can just see mesh over makes use of complete IP for routing, whereas mesh under uses data link layer for routing. In the sense, madam, how data link layer can be used for routing? Definitely not all aspects of data layer. Some functionality of data link layer is used for routing under mesh under approach. Okay, whereas mesh over talks about completely IP taking over routing task. That's the definition. Now, moving on to the next adaptation standard, which is 6LoW. Till now we discussed about 6LoWPAN. Now we discuss about 6LoW. 6LoW, what does it do? 6LoW, as you can see, even this is also meant for adaptation. Okay, even this does adaptation for IPv6 networks. And you can just see it is intended for definitely 6LoWPAN over BLE, Bluetooth Low Energy. Okay, it is used for NFC, used in 802.11 AH. In a sense, adaptation of this 6LoW for IPv6 is done in all these technologies. Okay, Dectra, then you have WIA, then you have MS bar TP. In all these things, for IPv6 adaptations or optimizations, we use 6 low group. Next, we have 6-stitch. Even 6-stitch is also a standard. Okay, stitch actually is nothing but time slotted channel hopping. Okay, and even this is also an optimization type for IoT. Yes, and you can see that the description to it. Okay, you can find that the 6-stitch is used for IEEE 802.15.4E standard. And also you can find here that we have a working group specified for the 6-stitch. That working group is a role, okay, standing for routing over low power and lossy networks. This completely take care of TISH. So TISH is handled by two working groups, role and core. And now coming to the, please observe the TISH structure. Okay, top location of 6 top sub-layer structure. You have IPv6 network layer here. Please observe 6-low-PAN header compression is here, and between the 6-low-PAN and 6-stitch, you have 6-top layer. Okay, so 6-top is an additional layer used in 6-stitch. What does it do? It is residing between 6-low-PAN's header compression and 6-stitch data link layer. And you can see there are 4 types of management techniques in case of 6-stitch. One is static scheduling, wherein you don't have dynamic changes to be done. Once you fix the slot, you will have to make sure you perform the task within the scheduled time. And you have neighbor to neighbor scheduling. It's nothing but correlating between the nodes. One node correlates between the other nodes, mentioning its traffic requirements and bandwidth needs, depending upon which you will schedule whether it is allowed to be transmitted or not. And then you have remote monitoring and scheduling management. This is nothing but some equipment placed at a certain remote place, and it will monitor and decide whether you require the scheduling needs or not. And then you have hop by hop scheduling. This is nothing but reserving a particular path from source to destination by having these many number of hops, right? So this is how forwarding is done in case of 6-stitch with the help of these different approaches. Totally, there are 3 forwarding models in TRISH. One is track forwarding, fragment forwarding, and you have IPv6 forwarding. So what is this track forwarding? Track forwarding, you establish a track first, which is basically a unidirectional path from source to destination, and then you forward all the cells or data in a given schedule across this track. Okay. What about fragment forwarding? In fragment forwarding, I break the IPv6 packet into multiple fragments based on given payload and based on given maximum transmission unit source. Okay. And then I'll transmit these fragments one after the other. Whereas IPv6 forwarding, this is nothing but what you do is you classify the packets based on their priorities, based on their traffic requirements, type of service, as well as quality of service requirements, and then you forward them. Right. Next, what we have is RPL. We have a RPL here. Okay, RPL is nothing but a routing protocol here. So what does this do? It basically takes care of routing data between low power and lossy networks. As we told in IoT, we have the devices of constraint type and constraint networks. To forward data, we have special routing protocol here called as RPL. So in RPL, we have storing mode as well as non-storing mode, 2 types of modes. Okay, so storing mode actually has a full routing table for forwarding, whereas in non-storing mode we don't have complete routing table for forwarding. Okay, because it doesn't have that much of memory. It doesn't perform storing in complete form. Okay, it has only partial information about routing table. And this RPL is implemented based on the concept of DAG, which is directed acyclic graph. Okay, so here we'll see about it. Please observe. This is a directed acyclic graph. Okay, where there are no cycles and the graphs or the edges are directed, where the nodes are nothing but whatever vertices you can find, they're nothing but nodes. These are nothing but the links connected between the different nodes. And DODAG and DAG. These are nothing but 2 differences. What is DODAG and DAG? In DODAG, it's nothing but a DAG routed to one destination. Please observe. In this DAG, we have multiple destinations, 3 destinations. Whereas in this DODAG, I have a single destination. So if I reduce DAG to a single destination, it becomes a DODAG. So RPL works in the form of constructing a node for a given network, a graph for a given network, and after that implementing DAG algorithm as well as do DAG algorithm to find path to a given destination. And for this, it makes use of two types of messages, DIO and DAO messages. DIO stands for DAG information objects, okay? And DAO stands for destination advertisement objects. So these two are nothing but types of messages which are made use in order to construct a tree in case of RPL. Please observe here, okay? You can see this is a DAG route, okay? And there are nothing but different levels, what you cross. The levels are nothing but ranks. The nodes which are close to the DAG route fall into the top level rank based on the distance. As far the nodes are to the root, the ranks fall low. Okay. And this DAO and DIO messages are nothing but which move or forward both upside and downwards in order to set a path, shortest path from different nodes to the DAG route, which is your destination in order to be forwarded. And this RPL has certain features, like it has objective function as its own. It's nothing but metrics what you're using for selecting the routes. And it has rank. Rank tells the distance, how close a route is to the route. Okay. And it has its own headers. Okay. Header structures or header formats. And it has its own metrics, as we told, metrics for routing, maybe in terms of battery, maybe in the routing protocols suggested, subrouting protocols which you use. Okay. And some of the metrics what can be used for routing is definitely ETX, expected transmission count. It tells the number of transmissions a node should expect to make a packet to be delivered. Then hop count, number of hops you have to cross to reach a destination. Latency is nothing but the delay, what you incur. Then link quality level is nothing but reliability of the link, followed by link color. Link color is nothing but whether a link is more desirable or not to be used. Okay. Node state and attribute, state of a node and its attribute. Node energy in terms of its power. Throughput. Throughput is nothing but based on terms of link. Okay. And finally, what we have is some of the authentication and encryption performed on constrained nodes. We have two basic techniques or two working groups for performing security over these constrained nodes. One is ACE and DICE. ACE is authentication and authorization for constrained environments. So working group on security, it basically makes use of DTLS protocol with COAP for security. And you can see that DICE, DICE. So even this makes use of CAP protocol, okay, along with DTLS security to perform its secure operations. And moving on to profiles and compliances. So some of the profiles and compliances are for optimizing IP to IoT. We have IPSO Alliance, okay, and we have WISN Alliance. Then we have Thread, and then we have IPv6 Ready logo. So up to this is one part of the chapter, and moving on to the next chapter, I'll quickly go through it as we are running out of time. So application protocols for IoT, what all we have here. Okay, so we have transport layer and application description first. Okay, so as you all know, transport layer, basically two major protocols are used, TCP and UDP. As you know, the difference between TCP and UDP is discussed here. TCP is connection oriented and UDP is connectionless. TCP has guarantee of service and UDP has no guarantee to the data what you deliver. Okay, and if you can say TCP size in terms of its header, okay, and UDP size in terms of its header, right? Then yeah, what are the things you have? Application transport methods in IoT. Application transport methods are basically following into sections. One is application layer protocol not present, and super SCADA systems, as I told you, generic web-based protocol and IoT application layer protocol. That means in IoT, if I have to send the application data, okay, then how all can I do? Should I require application layer protocol? It says no, not always required. Or you can make use of SCADA for transmitting data, or you can make use of web-based protocols for transmitting data in applications for IoT, or you can use separate application layer protocols. These four are very important questions. Okay, so these four concepts is what we'll discuss a bit in detail. So in case if application layer protocol is not present, then what can I use, madam? How well can I send the data? Definitely it says that you can send or receive the data based on the type of devices. The devices will not have any protocol. You can automatically send the data and receive the data by using the lower level layer protocols. What are the lower layer protocols? We have data link layer, we have network layer. So those layers are enough to forward data. I need not have a separate application layer protocol. That's the first option. You can just see here. Okay. We will have a data broker converting to a format which is required. Please observe sensor readings of different formats, 2 bytes, 4 bytes, 8 bytes. These all are converted to a common format and sent to different applications. Who does this? Broker does it. Next option, I have SCADA. So that means what? No individual application layer protocol. SCADA systems can perform the translation or they can perform data to be sent in applications. How they can do? We have SCADA multiple protocols available. I'll just name few. One is Modbus. Then we have DNP3 protocol of SCADA. Okay, so these protocols, what they do is they are responsible for transmitting data from one application to another application in IoT. So you can just see DNP3, Modbus, then IEC, right? So these are nothing but a DLMS, or you can find, no, they are nothing but some of the examples of SCADA protocols who can send data from one application to another. Please observe here, tunneling legacy SCADA over IP is another important topic. What we do is tunneling SCADA over IP means SCADA is basically non-IP. Okay. And you have IP nodes. How do you tunnel between these two? Definitely, please observe, we have three scenarios here. First scenario says you make use of sockets between the routers and perform no changes on the SCADA server. Please observe, this side we have remote terminal units, which are nothing but sensors. They sense the data and send it to the routers. And from routers over IP, you will have to send it to the SCADA server. Server is non-IP, whereas these routers are IP. Okay. This data is somehow sent to the IP. But from IP to the SCADA server, when you're sending, what you have to do, you have to implement sockets. The sockets are nothing but they are acting as tunneling agents. Okay. These tunneling agents, what they let you to communicate between non-IP to IP. That is first case. In the first case, you will not modify the server, but instead you will use sockets in between. Okay. Second case, scenario B. If you just see here, in scenario B, it says that you make use of sockets, but you make use of additional software in the SCADA server. What is that additional software? It is called as serial redirector software, IP bar serial redirector software. This software is installed in the SCADA server. That means we are doing some changes to the non-IP device in order to communicate with the IP infrastructure. Getting it? So you can just see here it was serial interfacing because we did not do any to the SCADA server. But here, since we perform some changes to the SCADA server by installing the software, I'm making use of normal IP network. Coming to third scenario. The third scenario, what we are trying to do, we are trying to make establishment between what? Direct communication between IP as well as your SCADA server, but your SCADA server is completely modified with applications of socket as well as TCP IP ports. That means I'm completely modifying here. There previously only one software was installed in your SCADA, but here what I'm trying to do, I'm trying to set up my whole SCADA server, trying to convert it from non-IP to IP. So three changes what I can do. Okay. Next, you have SCADA protocol translation. That means how SCADA translates different protocols. Definitely for this is the main picture. Gateways. Gateways should be used in order to perform SCADA different protocols translation. One protocol to another protocol, if I want to translate the data, then I have to make use of gateways. This is about a gateway, SCADA protocol translation. And yeah. I'll come on with the generic web-based protocols. So in this case, if I want to transfer data between different applications, I can use certain web-based protocols. Basically, which are the web-based protocols? As you all know, I have HTTP, I have XML, I have HTTPS, and so on, right? And sometimes even your telephone service providers can be made use. 3G or 4G networks can be made use, right? So they can be used for transmission of data between different applications. Finally, moving on to application layer protocols. So here we have two major protocols, CAP and MQTT. Not only CAP and MQTT, we have XMPP, multiple other protocols to be studied, but majorly these two are the IoT application layer protocols. CAP is constrained application protocol. This is the structure of CAP protocol. They are at the application layers. Bottom layers are quite common. Okay. CAP protocol. So you can see the description of CAP protocol is found in all these RFC numbers, description of. Also, you can just see the structure of CAP protocol is like this, message format. Very important question, message format. These are nothing but the fields of CAP protocol. If you go to explain, the first field is version. Second field, T, what you can find here. Now the T is a type of message. What you have, 4 types of messages are found in CAP. Okay, and you see here it is token length. Okay, length of a token, followed by the code. Code indicates whether it's a request message or a response message, followed by the message ID, and you have token length, what you had specified. Here is the actual token, which tells whether it's a request or response, and you have certain options field, followed by the payload field where your content is deployed. Right? And if you can just see, CAP has 4 types of messages we told just now: conformable, non-conformable, acknowledgement, and reset. Okay, so these 4 types of messages is what we indicated. And here is a diagram which tells you CAP supports reliable transmission with the help of DTLS. CAP is insecure, but we use DTLS to make it secure because CAP operates on UDP, MQTT operates on TCP. Okay, so here you can see temperature sensor you have, and it is reading sensor values. Okay, and it is sending the data with the help of CAP message. And client, whenever he wants, he can extract data by using GET request. Okay, so GET request, HTTP GET and POST request are being used. CAP operates similar to HTTP protocol. Okay, whenever you want, you can request so that the sensor responds to you with the data, whatever you need. Next protocol is nothing but MQTT. So this MQTT is reliable when compared to your CAP because it operates over TCP. Okay, and if you can just look out for the method of working of MQTT, it follows publish subscribe mechanism. What do you mean by publish subscribe is publisher will have and you will have a subscriber, and between them you'll have brokers. Okay, publisher is one who has the data and who generates the data. He does not directly communicate with the subscriber, but he in turn publishes his data to the broker. Broker, upon request and upon subscription by the subscriber, he will forward this particular content, whatever he has. Okay, so this is publish subscribe mechanism by MQTT, whereas your CAP follows client server mechanism. Okay, so this is our additional description, and this is the format of structure for MQTT message format. Okay, and say you can find some of the message types used in MQTT. Different message types are here. You can just look out 3 quality levels: quality of service levels, quality of service 0, quality of service 1, and quality of service 2. Okay, and you can just look out the diagram what it depicts: 3 quality service layers. You can just see quality of service 0 tells delivery at most once to the data, and quality of service 1 says at least once you'll deliver the data, and quality of service tells exactly once you'll deliver the data and measure the service of quality. And these are nothing but differences between CAP and MQTT. Very important question, students. So differences in terms of chart. This chart, if you remember, that's enough. Please observe. Transfer protocol, CAP uses UDP, MQTT uses TCP, and this uses request response, whereas this uses publish subscribe. And here it is excellent, and here it is low or fair in terms of effectiveness. Security, it is insecure, whereas so DTLS is used. And MQTT, we use SSL or TLS. Communication model is one-to-one, and here it is money. It is lightweight CAP, whereas the MQTT is a bit heavy because it is reliable and it is uses TCP. And weakness, if you can say, it is not reliable because it uses UDP, it is not reliable CAP, whereas MQTT is found to be reliable when compared to your COAP, right? So these are nothing but some of the differences. And with this, we come to end of your module 3. Okay, so up to here is what I have described you or have given you a glimpse of the overview into the 3 models. Okay, I know by this 2 hours of time, it would be very tough for you to catch, and it would be definitely tough for me also to complete up all the portions. I had to run some of the slides. Okay, so any other questions if you have to discuss, it's allowed now.
Uh, if you want to ask questions, you can unmute yourselves and ask. And I see one question in the chat window. Can you throw some light on hijacked access points?
Sorry, sir. Yes, once again, please repeat.
Can you throw some light on hijacked access points?
Hijacked access points. Yes, sir. Actually, I would reply to that. See, the hijacked access point is right now not under the part of the study. Okay. So in the sense, the content what I am supposed to deliver, the talk what you have asked the question on will be separate. Okay, that point talks about security, right? So that point talks about security and the vulnerabilities what you have to be prone on different equipments of IoT. That would be a different study, sir. So as of now, that would not be covered in my part. Maybe if other time permits, I may take on separate session on it and then describe about it. Yeah.
I hope it got answered. So if the students have any other questions, you can unmute and ask. We'll wait for 2 minutes. And then if there's no questions, we'll end. Uh, so on behalf of IEEE Bangalore section, we thank Subhashini ma'am for delivering such a wonderful lecture. And I hope that it will be useful for the students for the exam preparations. Thank you so much, ma'am.
Yeah, thank you, sir. It's my pleasure. Thank you all the participants for joining. Thank you.